Welcome to Living Proof, the Isaac Newton Institute podcast. My name is Dan Aspel. Today's guest is Professor Kevin Buzzard of Imperial College London. Inspired by a lecture given by Thomas Hales at INI's Big Proof programme in 2017, Kevin has spent the past 7 years working with others on the Maths Library project. He'll explain all about it in detail over the next hour, including how it interacts with his recent 5-year grant to check the proof of Fermat's last theorem. We hope you enjoy the episode. So Kevin Buzzard, Professor of Pure Mathematics at Imperial College London, it's a real pleasure to have you here. Welcome to Living Proof.
Thank you very much, and hello.
So the reason why we're talking today, and I will have mentioned this in the intro, we'll begin by talking about the fact that you're working on building a maths library. And my understanding of this is that it will help the automation of finding proofs of mathematical theories. Now, actually, if I look at your profile page on imperial.ac.uk, you say, I believe that within my lifetime, computers will be able to help human mathematicians to create proofs, and I'm actively trying to accelerate this process. That seems like a great intro to it, but I would just love to hear from your point of view what all this means.
Okay, well, the first thing I should say is it's not just my library, and this is a very important fact. This is a free open source library that anybody can contribute to, and indeed many people maintain this library, and I was not even one of the maintainers of that library until a few months ago. So it's very much not my library. This is a project that's just happening on the internet to build a one coherent place where all of undergraduate and now sort of master's level mathematics is covered. And the idea is that it's no different to a collection of textbooks, apart from the fact that everything's been checked by a computer, so there's no mistakes. So and now we can sort of discuss what do we mean by are there definitely no mistakes or whatever. But to be quite honest, instead of going into all that sort of technicalities, I will just make the observation that many times you see comments in books or papers, and you type them into the computer and the computer says no, and every single occasion it's the computer that's being correct. And so if we just leave it like that, then what we're making is a maths library that's sort of superhuman in its accuracy, in the sense that it's doing a better job than all of the textbooks. But that's not why we're making it at all. I mean, obviously, human mathematical literature has errors in, and 99.9% of them are completely unimportant and are easy to fix. That's not why we're doing it. We're doing it for lots of reasons, but one of the reasons that motivates me is because we are digitising mathematics. This is the idea. We're not writing in LaTeX or English. We're writing code in a computer language which corresponds to mathematical theorems, but the advantage of writing it in code form is that then computers can read it, and computers can attempt to learn from it, and they learn in a different, they will learn from it in a different way to the way they learn from reading. Of course, computers read human text all the time. These large language models are trained on a huge body of human text, but when you train them using this way of explaining mathematics, they learn it differently. And in some sense, what I would hope that in some sense what's going on is that they're closer to, quotes, understanding it, whatever that means. I mean, it's not entirely clear that a computer can, quotes, understand anything. It's sort of like asking if a submarine can swim. It's sort of a slightly funny question. Maybe understanding is something that's intrinsic to humans, and you have to use different words for computers. But computers can they see details, and they see technical details and precise arguments in a way that they don't see when they're reading the human literature. And so that now, with the advent of AI and things moving very quickly, this simply raises the question as to whether computers will at some point be able to help human researchers do mathematics. I'm not talking, obviously they help us do if you want to work out the product of two 20-digit numbers, then you do that on a computer straight away. But this is helping mathematicians in a new way. This is helping mathematicians, hopefully, one day, it's helping mathematicians to do mathematical research and to prove new theorems. And then, of course, the ultimate dream is that these systems eventually get so good that they start beating us at mathematics. Like they beat us at chess, and they've beaten us at, they've beaten us at all board games now. And the question is, will mathematics be next? And you kind of think, well, maths is sort of defined by rules and it's a completely logical thing. So actually maths is very similar to a board game. But of course, the big difference is that the first mathematical object you learn, the counting numbers, goes on forever. And board games are very much a finite thing. So mathematics goes on forever. So the usual tools we use, we solve chess we became superhuman at chess. Computers did 30 odd years ago, like over 25 years ago. But those techniques don't just immediately apply to mathematics, because it's a one-player game, not a two-player game, and it's played on an infinite board is the easiest way of summarizing it. So computers can't sort of play against themselves to get very, very good. They can sort of try and prove and disprove simultaneously a theorem, but they might sort of generate a lot of rubbish and not really know if they're going anywhere. So we need new ideas, which will have to come from computer science, but we also need mathematicians to actually explain what is known, because we left the computer scientists for 25 years, and somehow in that, or more than that really, the systems we're using have existed for decades, but computer scientists never really sat down and developed one sort of coherent undergraduate mathematics library that covers everything that we teach to the undergraduates at a typical UK university. Such a library didn't exist 7 years ago, because somehow the computer scientists were interested in using the software to do different things. They wanted to do things like check computer-assisted proofs, like the four-color theorem, which is also a very important thing to do, but it's not what we wanted to do. We wanted to do things like get machines to understand what the undergraduates are doing, because that's surely a necessary prerequisite for understanding what researchers are doing. And there were, at the time when we started, there were completely basic undergraduate level results, which had never been taught to any of these computer systems at all. So that was sort of where we started. In fact, there was a lot of undergraduates involved at the beginning. It was quite extraordinary, really. There was a lot of very young people. In fact, the trick was that undergraduates didn't know any better, right? In 2017, this idea was considered completely zany. Like, why bother teaching a computer an undergraduate, at the time, sort of basic first and second year undergraduate level mathematics, because it's all completely standard and there's perfectly adequate. There were all sorts of reasons as to why this was a non-starter. You were never going to get to research level mathematics, because research level mathematics involved so much mathematics, the interesting stuff, that how are we going to get there if it's just a crowd of random people on the internet typing in basic theorems about groups and rings and vector spaces? But somehow the project ended up with a sort of pretty constant and sort of slowly increasing momentum. And then COVID happened and everyone had to stay in their houses. And then it sort of then it increased even more, because people were like, oh, what shall I do now? I can goof around with this kind of crazy maths library project. So the maths library project, Mathlib, is the rather uninnovative name, has just went from strength to strength during COVID. And now it's this really robust platform. And we have substantial evidence that there are certain results in the modern mathematical literature, things that have just been proved in the last couple of years, where you can just sit down and you can teach that proof to the computer, because all of the foundations are there.
Yeah, I can sense your sort of interest and passion in this. It's really interesting to hear about how it's grown over the last sort of 7 years or so. This may be a sort of an obvious question, but it seems to me that you this has not been approached with a sort of a very specific end goal in mind. It's been more a case of, this is an interesting thing to pursue and the possibilities of it are varied and great. And that's how it's developed. Is that fair to say? Or do you have something in mind that you would ideally like to achieve with it?
I would say that is a really, really, pertinent observation. At the very beginning, there was just a small number of people. I'm not in charge of this library, but I was there at the beginning. I defined the complex numbers. That was my first foray into this world. I defined a complex. I learned what a complex number was in 1987 from Alan Baker, the great Fields medalist Alan Baker, who was lecturing second year complex analysis, and he defined a complex number to be a pair of real numbers. And I thought that was a very elegant definition, because my school teacher had attempted to motivate them by talking about square roots of -1 and drawing pictures and things like this. But at the end of the day, that's sort of the feeling for why complex numbers exist. But at the end of the day, the definition of a complex number is it's just two real numbers, the real part and the imaginary part. So that was where I started, with very, very basic stuff. And at the time, I was just thinking, wouldn't it be great if we could just, have something where I could begin to contemplate proving Fermat's last theorem? Because I'd learnt, I was a student of Richard Taylor, who was a student of Wiles, and it was Taylor and Wiles that resolved, Wiles made the announcement at the INI in, must have been 93. And then the proof had a gap in, and it was fixed in 94. But I was a PhD student at the time, and when I was a postdoc, I spent sort of months of my life just devoted to reading the proof, because it was like an incredibly fashionable, important thing that had happened in my area. So I had to be on top of it. So I've always been aware of what kind of mathematics goes into that proof. And it's a complete, it's an absolute wealth of, it's like there's algebra, there's analysis, there's topology, there's geometry, there's arithmetic. There's just so many, there's a bit of combinatorics, there's lots and lots of things from across pure mathematics. And by the end of 2017, I'd looked at the kind of things that were available in this domain, this sort of computer theorem prover thing. And it was completely clear that something very different was happening. That like people were just developing a small theory, possibly independent of other work, and writing a paper and publishing it in a computer science conference proceedings, because that was somehow, that was how things worked in computer science. And there didn't seem to be one, classical development of mathematics. So I personally wanted it because I thought it would be a really interesting thing to do. It wasn't until a few months after this big proof conference that I suspect we'll talk about later. But it wasn't until like the end of 2017 that I realized what kind of a, in my view, what kind of a mess the area was in. I mean, people were using it to do things, but they weren't using it. What they were doing wasn't going to help me prove Fermat's last theorem. So my personal take on it was, wouldn't it be great if we could make some machine that could kind of understand what was happening in modern number theory? But to do that, you have to understand what's happening, at a sort of a basic graduate and MSc level in everything. So that was my motivation. But other people were just doing it. I mean, it was just an open source project that was available on the internet. People would make pull requests, and the maintainers would review them and merge them if they thought they were relevant. And at the beginning, the goals were very clear. We had nothing. When I started, we had definitions of finite sets, groups, rings, fields, and topological spaces, and that was it. And now the question is, what can you do with all of that? And one answer is, well, you can prove all the theorems I learned as an undergraduate. But that was going to be a huge amount of work already. So I got my undergraduates to start helping me doing that. And other people got involved to do other people were sort of specialists in one area and just kind of thought, I want to build this area. There was a guy, Kim Morrison, was building category theory at that time, and they were just building with no obvious application in mind at the time. They were just building category theory. That part of the library was getting bigger and bigger and bigger, and then there was sort of undergraduate level mathematics was also growing. And then at some point, the maintainers were like, what is this? This is completely ridiculous. Like, what is our library doing? We've got all this basic undergraduate stuff. Then we've got this completely different folder that contains a huge amount of category theory that's completely unrelated to the undergraduate stuff. And so maybe we should split our library in two. And I'm like, no, let's not do that. Because by the time we get to algebraic geometry, and we will get to algebraic geometry in a year or two, then category theory is going to become essential. So we need everything all in one place. The computer scientists were always ready to break things up into small pieces, like do one job and do it well. That's like do one job, do it well, and maybe get a paper out of it. And then leave the code alone, and then it stops compiling because it only works with some version of the software when the software's moved on. And now you can claim at the end of it that you've got all of these areas covered, but with sort of competing libraries that have competing definitions and might not even, compile together at the same time. So I was just in the background going, it's got to be one big library. In some sense, that was my main contribution. But of course, other mathematicians were coming along. The area just slowly grew. Patrick Masseau was also another person who was there at the beginning. He just realized that one thing that needed to be done is there's a huge amount of Bourbaki needed to be typed in to these systems, even though we don't teach people Bourbaki, but it was somehow doing the mathematics in the right generality. So he was working hard on Bourbaki, and then I did schemes, which I thought would change the world. I was going around telling all these algebraic geometers I taught a computer what a scheme was. A scheme is a basic building block in Grothendieck's algebraic geometry revolution in the 1960s. And I was super excited by this in late 2017, early 2018. We taught a computer what a scheme is, but everybody was just like, well, what's the point of that? I knew what a scheme was when I was a PhD student. So it was funny at the time. There was still a lot of people that just couldn't see the point of it at all. But I got completely addicted to the software. That was one thing. I found doing mathematics in this way much more exciting than doing it on paper, because it just kept track of everything. Sorry, you were going to say something.
I was only going to say that, is it fair to define this project as trying to create a single maths mind? You are trying to create something, a program, a machine, which is fluent and capable and creative with all mathematics. Is that?
Yeah. Well, computers are really bad at being creative. If this is something. The other question is, how far is it going to go? Right. At some point, we'll have to stop, or we'll have to define. This is an ongoing topic of debate. It's like, where are we going to stop? Because what we can do now is we can use what we have as a basis and put another project on top of it. So there've been, for example, Bhavik Mehta has been proving theorems from 2023 in combinatorics, but he doesn't put them in the library. He makes another project that has the library. It uses the library, but it's not in the library. And similarly, Terry Tao, his project with Tim Gowers and Green and Manners on the polynomial Freiman-Ruggie conjecture, they proved a theorem in late 23. And Tao announced that he was going to now teach this theorem to the computer, but it's not in the maths library. It's in a different project that has the maths library as a dependency. And so it is becoming a maths mind, but somehow you can't put all of mathematics. I don't think you can. I mean, I'm not a computer scientist, but all I know is that our library has 1 million lines of code, but I don't quite know whether it could have 1 billion lines of code and still sort of exist in the form it exists now. So it's becoming a maths mind, but I don't know what the limitations will be, and there must be limitations.
Yeah, and thus my next question, which as I play it through my head might sound a bit silly, but I'm going to ask it anyway. It will test your faith in its limitations. Let's say the year is 2080, and you are coming to checking a proof of a theory. What would be different to you or a student of yours in that distant time compared to today, should this project continue at its same pace or greater? What difference will it make to the lives?
Are you talking in 50 years time?
Mm-hmm.
Yeah, I can't answer those questions. Having spent a lot of time talking to in the last 7 years, I saw something that looked completely impossible happening. And so I wouldn't like to predict what can happen in 7 years time, let alone 50 years time. But let me go for 10.
Okay.
I feel more comfortable conjecturing about what will happen in 10 years time. There's this sort of running joke in this whole AI area is that it's extremely easy to predict what will happen in 10 years' time, because it always sort of moves. You can, people say, oh, in 10 years' time this will happen, but they tend not to be recorded when they actually said it. So this is
that's the danger of our conversation.
Yeah. So in 10 years' time from now, 2024, I'm hoping that at the very least we have a system which, let's say, let me give you my minimal, I'm an AI pessimist, but maybe minimally we will have some kind of system which will be useful to graduate students. Let's just take that as a goal that some computer scientists will laugh at and say it's ridiculously unambitious. But if I have some kind of tool where my graduate students need to learn algebraic geometry, or they need to learn, arithmetic geometry, or some technical area of modern number theory, I can say, oh, it's all right. You can use the AI assistant that is not just ChatGPT or some generic thing, which is quite good at giving generic advice, but might be a bit rubbish at the details. You'll be able to use some kind of hybrid system, which is, you won't have to learn how to use the software is complex, right? I can show a PhD student a maths proof written in LaTeX or in a book, and then I can show them the corresponding lean code, and the PhD student will be able to read the maths proof, but will be bamboozled by the lean code because they didn't go to my course when they were an undergraduate. They foolishly skipped my course, and they didn't sort of learn about the basics of how this language works and how to translate to and from. But you see, a translation task translated between the kind of mathematics that mathematicians are trained to read and this computer code that the computers can read, but which sort of represent the same ideas. Translation tasks are things which computers do extraordinarily well, right? They can translate between English and Chinese, very, very accurate. They were very, very good a few years ago, and then they got even better because of new techniques in machine learning and things like that. So in 10 years' time, I would imagine that these things will just be translating between the two languages. The difficulty now is that there's an awful lot of language on the internet, but there's very little of this computer language that I'm writing on. There's not enough to become really, really good really, really quickly, because there's just simply a lack of data. But the data in 10 years' time, people are already talking about generating synthetic data, getting computers to write code and then somehow training on this code. It all sounds a bit pie in the sky to me, but I'm not an AI expert at all, and it wouldn't surprise me if within 10 years this has been solved, and we'll have a computer. The PhD student can ask a question in the language they know, because I don't think we're going to force all mathematicians to learn this esoteric programming languages. I think that's a no-go. The graduate student writes in the language they know. This is now translated into Lean, this computer language, and then we can start looking through the library, or asking various AI assistants to say, how could we go about proving this? Is this theorem true? We've got a database of counterexamples. Can we find a counterexample in our big list? And then we can hopefully, then the output to the student is, the question you're asking about, here's a good place to read about it. Here's a proof of the theorem you were hinting at. Here's a natural looking generalization of the theorem, but that's false. And here's the counterexample. You get something. Now, that's exactly what the PhD student wanted to hear. They got this sort of general idea about a theorem in a general area, and then they come out sort of having an overview of the area, good reference, references that exist, right? Because large language models just make references up. But the idea of tying language models into theorem provers is that then they don't get to make things up, because the things they say should be sort of being checked behind the scenes by the computer.
So you have this, essentially have this amazing efficiency gain for learning. So
that's what I'm hoping, is that it will be useful for learning. But you see, now let me tell you the optimist view, is that in 10 years' time, the systems, you'll just be able to pick up the textbooks. I've just got a random graduate text in mathematics on my desk here right next to me. In fact, I've got two. The idea is you just feed that into the machine. You get the LaTeX, you feed it into the machine, and the proofs come out, and the machine just knows everything. So the machine has already digested a huge amount of human literature, and now it's sort of going away autonomously, proving theorems by itself. So this is what some people who are computer scientists who know much more about the way AI is going than me. And as a mathematician, I'm slightly nervous about these audacious predictions, not because I'll be out of a job, because that's what I'm working. I'm working towards making a machine that will be better. I'm working towards early retirement. That's the whole plan. But I'll tell Imperial that they can just use this machine instead, and it can prove much better theorems in number theory. But what I'm concerned about is that I saw Wiles's proof of Fermat's last theorem, and this was suddenly a big step change. Suddenly we could do things we couldn't do before. And then by 2 years after that, people had had other ideas as well, and there'd been other step changes. And by sort of 7 or so years later, Wiles had techniques that worked for 2-dimensional representations. We had techniques that worked for n-dimensional representations. We proved much more than he had proved. And there's been this flurry of activity. And now we had new techniques, and we kind of understood how far they would go. And then things kind of calmed down a bit. So there was activity and then calm. And the computer scientists seem to think, this is my impression, is that because there's a huge amount of activity in AI and language models now, then just by extrapolation, that will just continue forever. And we're on some exponential curve and blah, blah, blah. And I'm just thinking, well, sort of in my line of work, that's not how it works. You get these exponential jumps that then sort of tail off. And so in 10 years' time, part of me thinks that maybe in 10 years' time, language models will just be sort of passé. We'll know what they're good for. We'll use them, we'll use them as chatbots for when you have problems with your gas bill. And we'll use them as aggregate. You don't want to Google something. You just want to know all about it. You'll use it as an aggregator, much as we do now. But they won't actually have got any better, because it turns out that we couldn't make them learn anything, and it turns out that we couldn't stop them making things up, and so they're regarded as unreliable by scientists. So I don't really know what's actually going to happen, but as I say, my completely pessimistic view that we'll have some tool that can help graduate. That's the absolute minimum of what I believe. We'll definitely have some tool that I'll be able to use with PhD students, and ideally we'll have some tool that I'll be able to use myself. It's like, just this diagram commute. I just type the thing into the computer, and the computer will actually work it out for me. I think that's also, not completely impossible within 10 years. But I'll tell you, the big problem now is that right now the systems still don't understand the definitions. We're 7 years in to this amazing project, but right now we still don't have the definition of an automorphic form, which is a technical thing in the Langlands. It's the basic object of study in the Langlands program. So you can ask yourself, well, the Langlands program, that's very trendy. People do lots of work at the Langlands program. Will systems be able to prove all the theorems in the Langlands program in 10 years' time? And my take on this is, I'm hoping that in about 5 years' time, the systems will be able to understand the questions. We'll be able to state the theorems, you see, and for me that's not completely obvious, because right now definitions are hard work, and the definitions are all being done manually, and I wouldn't trust a computer to translate a mathematical definition into this language. I'd trust the computer to do, if I've got all the definitions fine, and then the computer translates a human proved theorem into this computer code and the computer code compiles, then that's great. But if it's proved theorems about things that have been defined incorrectly, then you're in trouble, right? You might sort of. So the definitions are they need to be human checked very carefully. And right now everything is highly manual, and I think will remain so for the next few years. And so, one of the projects I'm involved in is, as I've mentioned Fermat's last theorem several times already. I'm involved in the beginnings of typing in the proof of that theorem into the machine, and that will involve teaching the machine a lot of definitions of sort of modern objects in the Langlands program. So will they be proving things in the Langlands conjectures? I mean, I don't think they'll be doing that in 5 years' time, however good AI gets, because I don't think they'll.
I'm right in saying that you have a 5-year grant.
Yay!
To check the proof of Fermat's last theorem. So am I right in saying that you've said before that you believe that to be a sort of 30-man-year project? I 5-year grant.
I don't think I'm going to be proving Fermat's last theorem in 5 years, but I think that 5 years my conjecture is I can formalize the ideas in the papers by Wiles and Taylor. I think that I can do that in under 5 years, to be honest. But that was what went into the proposal. Just take the breakthrough papers that prove Fermat's last theorem, and see if I could translate them. But those papers are full of references. So in fact, I'm not going to prove exactly what's in the papers. A lot of things have happened since then. The arguments are 30 years old. So I'll give a more modern, streamlined, slick proof that basically Richard Taylor explained to me in discussions with Taylor. We've come up with some modern argument, but I still need references. I still need old work of Langlands and old work of Maser, things from the 70s and 80s. And I don't think 5 years, and basically for the whole thing to get done in 5 years, I would need to find other people that would be prepared to devote 5 years of their life to sort of formalizing these references. There's no known proof of Fermat's last theorem that avoids some of these basic standard references from the 70s and 80s. So what I'm going to do in 5 years is I'm going to reduce the proof of Fermat's last theorem to something that was unknown in the 90s, in the early 90s. I'm going to reduce it from something that was known in the 90s to things that were known in the 80s.
Yeah.
And then I'm going to need other people to sort those out, especially the work of Langlands, because this is hard analysis, and I'm not a great analyst. I've plowed through some of this stuff, but I find integrals terrifying, especially the kind of integrals they're using in the trace formula. So I'm saying that there is a roadmap towards humanity teaching a computer a proof of Fermat's last theorem. But it's whether humanity actually gets around to doing it. You see, another possibility is the computers just get so good that after 5 years, it's just observed that I completely wasted my time, and you just take the papers by tails and miles and feed them into the machine, and it does it for me. Right? That is a possibility. But
again, very much the optimist's view.
The optimist view. I think, to be quite honest, I think it would be very interesting to see where we are. The grant starts like a week today, I think, a week tomorrow, and 1st of October, and it will be very interesting to see in 5 years' time sort of where we are, and whether we can see a roadmap to actually finishing the job, and how much of it will be done autonomously by machines. But I just really don't know.
Here's a slightly impressionistic question, if that's the right word. But if you have the definitions well sorted for the machine, and let's say that your optimistic view turns out to be true, and ultimately the maths library is capable of infallibly, for want of a better word, confirming or disconfirming proofs of theorems, do you as a mathematician, or does humanity and its practice of mathematics lose anything that way, or is it all gain by offloading this job?
I would argue that in some sense we're not losing or gaining anything. I mean, if we're gaining, I already know the proof of Fermat's last theorem is correct, right? So the fact that a computer then says it's correct, I've gained nothing. That's not what motivates me at all. And in fact, this is what's different to what was happening 10 years ago. 10 years ago, people were checking proofs that were in some way contentious, because they might have a component which computers generated, and the computer code might have bugs. I'm certainly not doing this because I think that the proof of Fermat's last theorem might be wrong. Although, funnily enough, we have found a mistake in it already. I mean, we found a mistake in the route that I was taking, but it's been fixed now. But ironically, there's an absolute howler in the literature, which was sort of went unnoticed, and then there was another paper released like literally 15 years later that said, oh, instead of plowing through this 200-page monograph, here's a sort of a summarized sketch of how it all works, and the summary didn't have the error in. So there will be errors that we'll find that will be quite funny, but there will always be fixable. This is the thing. There was a theorem which is correct, and the theorem relied on a lemma, and the lemma was incorrect. It was a genuine mistake in the literature, but the theorem is correct, because if the theorem is wrong, then mathematicians would have noticed decades ago. So we will find, there will be other funny stories of this nature, but that's not really the point. The point is that if we want, the dream goal is getting machines to prove theorems in the Langlands philosophy automatically, right? And that's where we're going. That's where we're going. So the sort of the proof of Fermat's last theorem thing. This is another publicity stunt, right? It's all about the publicity stunts. This is something that I thought would be interesting. The media would be interested because it's Fermat's last theorem. It's on the front page of the New York Times and it's proved. It's a very concrete goal. I think it's an attainable goal. I think it will be a lot of hard work. But I think what we will have when we've attained it is just nothing. In some sense, we will have a proof that humanity can now do something that 10 years ago looked completely out of reach. Right, that's what we'll have. But will we have a better understanding of Fermat's last theorem? I would like to think that I will have a more conceptual understanding of Fermat's last theorem at the end of it, because when you type this stuff into the computer doesn't like ugly proofs. Ugly proofs take a long time to code, and it's sort of slow and tedious, and the proofs take a long time to compile. You always want to find the more conceptual argument. So I find this quite exciting, because that wasn't my mindset when I was reading the proof as a postdoc in the 90s. My mindset was like, get through by any means possible. It doesn't matter if this proof is grotty. It involves some ugly technical lemma that we don't really care about. But we just want to make sure that everything glues together. But now I'm just thinking, no. I don't want to be typing in grimy technical lemmas. I want to find the conceptual way of doing everything. So I might, at the end of it, be able to, write a nice paper that says, we all know the proof of Fermat's last theorem, but here are sort of 5 things that I learned along the way. Here are 5 standard results, but actually here are more conceptual ways, or 10, or however many, or 100, however many times it happens to me. So I'd like to think I'm making the proof of Fermat's last theorem more beautiful. I'm also digitizing the proof. Digitizing things is really important. We digitize music. I couldn't see the point at the time. That was also happening in the 90s. I had all this vinyl, and all of a sudden people were telling me to buy CDs. And I even knew people that were buying CDs of vinyl that they already owned. And I was just thinking, this is just like the man ripping us off. But the underlying point of CDs, I somehow didn't realize this for a long time. It wasn't that we were just, they were forcing us to buy another product. It was that we were digitizing music, and you digitize music, and now all of a sudden you can send it via the internet, which is just, obviously can't send vinyl by the internet. You can send it by the internet, and now we have Spotify, and that sort of completely changed everything. So digitizing music marked a massive change. It took a long time, but ultimately it marked a massive change in the way music is consumed, in the way music is sold, in the way artists make their money. It really turned the music industry on its head. And I think it's not sort of a stretch, too much of a stretch to argue that digitizing mathematics certainly has the potential to turn mathematics on its head. And so formalizing the proof of Fermat's last theorem, I'm just somehow saying, look, we can do that, therefore we can do anything. This is the proof, because the proof involves algebra analysis. As I've said, it involves things from all over mathematics. So we're proving that we have a system that can definitely do all of mathematics at the required level. This is what we're going to get. I don't think we'll learn it. At the end of it, if I tell Andrew Wiles that I can prove his theorem, he'll be like, well, I can prove my theorem. And that would not be an unreasonable response. Right. But what we're doing, the goal is not to prove Fermat's last theorem. The goal is to somehow make tools that, together with AI techniques, will turn mathematics on its head. And obviously that's yet to happen. So I can't say we've done it. This isn't a success. It's currently an experiment, but it's blue sky thinking. It's blue sky thinking in the same way that I spent 25 years working in the p-adic Langlands philosophy, and that was just absolute, blue sky thinking. There were no clear applications, and really no hint that there could be an application of this work to the real world, even in the next 50 years. But it's sort of abstract, very beautiful abstract stuff. It's giving us a better understanding of how the mathematical world fits together. And because of that, because of those kinds of thoughts, that's why this stuff gets funded. And I'd like to think that our crazy computer maths library is the same thing. We're building, we don't quite know where it's going, as you pointed out. I think different people have different goals anyway. My goal is to get in all the prerequisites for proving Fermat's last theorem. but there's 25 other maintainers and of this library, and they will certainly have different goals. And even different visions as to where it's going. But the thing is, you're allowed to have different visions because you can just let the thing grow in more than one direction at once. So,
yeah, that's a fascinating way of putting it. What a great summary that was. Thank you. Thank you very much, Kevin. If I can ask, for those who aren't sort of familiar with it or don't work with it, can you tell me about Lean and how that feeds into the maths library?
So Lean is the language which the maths library is written in. The maths library can be thought of as a gigantic computer program. You could think about it two totally different ways. One is sort of a weird new digitized textbook that contains lots of proofs of theorems. And if you've got some mathematical training, then you can read the statements of the theorems and think, oh yeah, I can guess what that. You look at the statements and you think, yeah, okay, I can understand that. And then you look at the proofs and they're in this gobbledygook programming language. And the programming language is called Lean, and it's just it's a functional programming language. So that's a lot of programming languages that people learn are procedural, where the program just sort of follows the commands in the order it's given. But a functional programming language is a different kind of programming languages. Haskell is probably the most popular one. We teach functional languages to the first year computer scientists at Imperial because we discovered apparently that if you teach them Python, or kind of a language which is sort of important to in use in lots of places, then you end up with some kids that know everything already and some kids that know very little, and it's sort of a very difficult class to teach. Whereas if you teach them Haskell, then you can be sort of fairly confident that nobody knows a thing about it. It's a much more obscure language because it's functional. So Lean is a functional language, and these are sort of popular in computer science departments, but my impression is that there's not much actual functional code that's actually running things in the wild. So perhaps the point of functional code is maybe not to make practical applications, but to do things like prove that computer code is correct. Right? That's bugs in code. That's $1 billion industry, right? You don't want planes falling out the sky. There was this Intel thing in the 90s where the CPU couldn't compute division, extremely rare occurrences. It would give slightly the wrong answer for a division, and this caused a gigantic recall of every Pentium chip that had this bug in that cost like $500 million. But bugs in code are really serious problems, and so Lean is a functional programming language with this extra twist, which is what separates it from normal programming languages. That in normal programming languages, you can have variables which are numbers. You can let x be 7, or you can let x be a string. If you want to print, you can let x be hello. If you want to print something out, But and then your code manipulates numbers and manipulates strings and whatever, manipulates databases. So in Lean, variables can be numbers and strings, but they can also be theorem statements and theorem proofs. And that's the big difference. There's something in there that enables it to manipulate theorems in the same way that people doing computations manipulate numbers. You can add numbers up, multiply them together, and computers can do that. Well, if you're using Lean, then you can do things like prove that this theorem implies that theorem, or prove that this theorem is true. So that's what it has, is a different type of variables that are not normally present in a programming language. And just because you have that, when you switch it on, right, you download Lean off the internet because it's also free and open source, and then you switch it on and it knows the axioms of maths and the rules of logic, and that's sort of it. It has some good algorithms. If you want it to do things, then you can try some of its algorithms, but these algorithms are not really mathematical. It doesn't know what a vector space is. You take a basic mathematical object. It doesn't know what the real numbers are. These are two very basic mathematical objects. Those are defined in the maths library. So when you just switch Lean on, it has the capability of doing mathematics, but nobody taught it any mathematics yet. So that's what Lean is itself. But basically the idea is you write code, and if the code compiles, then it's correct. And one of the things computer scientists want to use it for checking code has got no bugs, because it can do that too. But then the idea is, well, can you also use it to prove that maths theorems are correct? And the answer is yes, except you've got to teach it maths first. So that's sort of the separation of the things. You've got the language and then the library written in the language.
Yeah, I can see why it was the logical choice then. That's a great explanation. Thank you. I guess I want to bring this back as we sort of near the end of our conversation to a point which I probably should have made as the podcast began, but that's fine because I'll mention it in the intro, which is that I think we can tie all of this to the Newton Institute's activities, because in 2017, there was a program called Big Proof. You attended that, if we can use that word, virtually long before it was fashionable, because this was pre-pandemic. You were able to, take part and watch some of the talks. And I believe that it was Thomas Hales's proof of the Kepler conjecture that was computer assisted, which formed a sort of inspiration to you before you began working on the maths library. Is that correct to say?
So, it's close to correct. I was certainly that INI conference, that Big Proof conference, changed my life completely. It's a very easy summary, because before that I was an algebraic number theorist doing things the normal algebraic number theory way, and as was I knew Hales. I met him in Harvard sort of 10 years prior to this, and so I was interested in his talk. I got interested in theorem proof because I thought I could use it to teach. I teach Imperial's Introduction to Mathematical Proof course, and it was summer of 2017, and I just taught it in 2016 for the first time in about a decade. And I kind of thought, I want to spice this course up a bit. And I thought, I wonder if I can use computer proof assistants to do it, because I knew of the existence of these things. There'd been an article about it in the notices of the AMS in 2008, I think. So I knew that these things existed, and I thought maybe I could use them to sort of spice up this undergraduate course. And then, so I'm just Googling around trying to work out what's going on. And one of the things I discovered was that in 2 weeks' time, there's going to be a conference at the Newton Institute on precisely this stuff. And of course, I associate I associated the area with computer science, but I associate the Newton Institute primarily with mathematics. I know it does mathematics and X or something, but at the end of the day, it's sort of it's mathematics. And so I was very interested in this workshop, but I somehow couldn't attend it because I had some commitments in London, and also I think it was too late to register for it. But yeah, I and I were ahead of this. Is 2017, right? This is pre-pandemic, but the Newton Institute were ahead of the game because they were live streaming everything. So I sat in my shed watching these talks, and the very first talk of the conference was by Hales, which wasn't just about this proof of the Kepler conjecture, which in my mind, you see, the Kepler conjecture is a very long and complicated proof about very, very simple objects, and really a lot of the other objects that go into the proof are sort of quite simple and low level. The Kepler conjecture is about spheres, right? Spheres in three-dimensional space, and a lot of what was happening at that time, they could have been very difficult theorems, like the proof of the odd order theorem that had been typed up into a coq by Gontier. But these proofs, a finite group is a very elementary object, and the proof just involves manipulating elementary objects. And Hales had a slide about doing modern, exactly what I've been talking about, doing modern algebraic number theory in these systems. And he put this slide up, and it just contained a list of 25 mathematical definitions that I was very familiar with, because he's a number theorist like me. And he just said, we're going to need all of this stuff, and none of it's been done. And I'm just staring at this list thinking, I've just spent 2 weeks goofing around with this software, proving things like the natural number, addition of the natural numbers is commutative, basic stuff about the natural numbers. But I could actually get my teeth into making these definitions because I know the mathematical definitions, and it's just a case of translating it into the software. At that time, I didn't even know which software I was using. But in a question at the end, Hales proposed making a system which was good enough to understand the statements of modern mathematics. This was his big vision, not the proofs, because that's far too complicated. He wanted a system where you could take the statements of modern mathematics and the system would understand the statements, and we could at least record formally exactly what people were claiming that they had proved. Because it's difficult to read papers, because you read papers and sort of in the third paragraph it says, for the rest of this paper, P will be an odd prime. And then you see this statement about the number P, and because you're a number theorist, that P must be a prime, because number theorists always call primes P. But you don't realize that a few paragraphs up, there was this remark that P had to be an odd prime, and it's not stated in the theorem. And so it's sort of, you might look at it and incorrectly assume that this theorem applies to the prime number 2. And this causes problems. This phenomenon is known to cause problems in the literature, but people quote theorems that look like they might apply, but don't apply because of remarks made earlier. So Hales's view was that we could solve this by making a sort of a database of mathematical statements. But he said we can't even do that because none of the systems out there even understand the definitions we're working with. And he put up these 25 definitions and said, here's examples of things that we're a million miles from. And then at the end of it, somebody said, which system are you going to use? And Hales said, I propose, my proposal is lean, he said. And that was the first time I'd ever heard of lean. So that was how the whole lean thing started. And I started by just beginning to work on Hales's program. And the first thing on his list was schemes. And so we did schemes, and it was a fiasco. Within 6 months of seeing Hales's talk, I'd defined schemes. Me and some undergraduates. I wrote a paper with a bunch of undergraduates. Again, that's another very exciting thing. And then I started telling the algebraic geometers, and they couldn't give a monkey's. They were like, schemes are a basic object. Everyone knows what a scheme is. It doesn't surprise me that a computer knows what a scheme is. And so my next project was I took the last thing on Hales's list, which was perfectoid spaces, and me and a couple of other mathematicians, Masso and Comelan. Masso independently had the idea, I should say. Within the same week, we came up with this idea of formalizing perfectoid spaces because we thought it would be, because they're very fancy, complicated objects. Most mathematicians don't have a clue what they are. And Peter Scholz was about to win a Fields Medal for proving theorems using them. And so we formalized perfectoid spaces. And that was suddenly when it all started happening. Then everybody was like, we had no idea the systems were this good. So again, it was a careful, it was a careful con trick, really, because we didn't prove any hard theories about perfectoid spaces, but we just had the definition. But somehow I could trace my idea of defining a perfectoid space in using this software. It was all back to this Newton Institute talk, and then we did that, and then somehow for the next 5 years, my life's been a crazy roller coaster. I've just got back I've just done a round the world tour. It's completely ridiculous. So that talk by Hales, I mean, I saw plenty of the other talks as well, but that talk by Hales really changed. It completely changed my life. I still identify as a number theorist, but now my goals are clearly very different to what they were 7 years ago. I can only thank the Newton Institute. But if you hadn't streamed it, I would never have seen it.
There you go. So it's a dangerous warning to anyone listening. Beware of what you watch at the Newton Institute, lest it change your life.
It could change your life, but it's changed it in a very good way. Like business class flight from Beijing to New York and 4-star hotels and chauffeur-driven cars. I'm living the life of the transformation of my life from second-rate number theorist to somebody that is been absolutely extraordinary. So you should definitely warn people not to go to the Newton Institute unless they want that to happen to them.
Yes, guaranteed result for every participant. And of course, coming up in October 2024, which as we record is only a week or so away, is the big specification program.
Oh yes,
month-long program which will address much of the same subject matter as big proof. So again, if you attend any part of that, who knows what will happen by next year.
Big specification is sort of really the practical. I'm interested in turning mathematics on its head. But there are one could hope that this software could also turn areas of computer science on its head as well. So who knows what we're going to learn there. Yeah.
Well, Kevin Buzzard, it's been such a pleasure to talk to you about this. I really thank you for your time. It's been really fascinating and passionate, and I hope that whoever's listening to this has gained as much as I have from it. I think there's so much to digest here. So thank you very much indeed. And I hope the rest of your day and week continues in the same energetic vein.
And 5 years.
Yes, indeed.
It is great. I still wake up every morning thinking I want to prove Fermat's last theorem. it's good. I mean, the grant hasn't even started yet, so it would be slightly worrying if I'd lost enthusiasm. But right now, I'm extremely enthusiastic about this project.
That's brilliant. Thank you very much. Super.
Cheers.